My name is Christian. I'm from a company called Moixia. It's an interesting name, but if you reverse it, it's Axiom, so it's not as complicated as it might seem. It's been a while actually since I've been in the JavaScript community, so I would like to gain a bit of information since I'm not entirely sure what the new cool things are. So like how many are familiar or doing TypeScript work? Yes. Okay, that's quite a few. And Flow from Facebook? Some again. Is anybody into PureScript? Okay. No one. Okay, so I was just interested in seeing like how familiar people are with type languages and stuff. Okay, so I work at the company called Moixia, and we are doing clean tech. So we are doing smart batteries, essentially. We sell batteries that goes into the homes of people, and they charge from solar energy or from the grid whenever it's cheap. They can consume that electricity themselves or push it back. So in that sense, we get a lot of events. We have chosen our stack to be written in Haskell. And how many people are familiar or at least heard about the programming language Haskell? A lot. Any people tried writing anything in it? Oh, exciting. That's perfect. So we actually chose to also use this on our front end. So actually compiling our front end to JavaScript from Haskell as well. So our entire code stack is basically Haskell, and we can get code share from the backend to the front end. So this is also going to be extremely interesting for me because I will need to interact with my computer quite a lot. So let's see how I will do that. Oh, and also I've been a contributor to I have like super big patches for the Professor Frisbee's Mostly Adequate Guide to Functional Programming. So I'm pretty deep into functional programming in general. Have anybody read that? Not really. Okay, I can recommend it at least. I hope. I hope you can review it. Okay, so why do I like functional programming? Well, it's because it gives me a different take, right? Nowadays, for me, most languages, I'm very interested in both academia, mathematics, and the area between basically academia and our industry. Because in order for us to progress and move forward, we kind of can benefit from each other's ideas. So I like finding something that some people have thought about for a long time and then applying it in practice. And I think that's a quote from Erling Perlis. Yeah, in general. So, whoa. Sorry. Like, if you learn a language that actually doesn't change the way you think, it doesn't matter at all. And basically, if you choose Ruby, if you choose JavaScript, if you choose Python, it's kind of the same nowadays. Like, it doesn't really matter. The hardest part about learning a new language most of the time is actually the ecosystem, what's available in the language. But picking up a language isn't actually that difficult. So your mileage may vary. And that's why I like values. Why do I like values? Because that's actually one of the few things that are transferable between languages. A map in any language is a map in any other language. So if you can describe your domain as data or in some way of shape as data, you can transfer it to the other language. So oftentimes, right, if you can just construct some data, you can do some transformations onto that. So today is about reactive programming, and I will talk to you about a specific implementation of reactive programming in a library called Reflex. And actually, as with many things, there's actually a lot of different implementations of things. On this list, I myself have actually used Bacon.js before, which I don't actually know if it lives anymore. But there's these different kinds of FRP libraries. So again, right, there's different pros and cons and benefits with everything. So take that with a grain of salt. So the basic premise of FRP from the original papers about FRP is basically there's two data types. They are the primitives of everything you're doing. They are events and they are behavior. Event is basically the observable that you know. Like it is something that produces a value over time. A behavior is something that always have a value, and you can sample that at any given point in time. That's why I've marked these as push and pull. Because an event is notifying somebody else, it happens, and somebody can react to it. But if some event happens, you can pull behaviors because they would have a value. The different thing about the library that I'm using here and I'm showing tonight is that they also have this data type called dynamic. And dynamic is basically a combination of both a behavior and an event. So you get both premises. I've actually written these three elements as the types as they are in Haskell. And you might be wondering what this TR is and what the A is. The T you can basically think about as timeline and ignore it for that. It just means that for each and everything that I work with, as long as it's the same T, it will work out. The A is generic, so it can be anything. So it could be an event of int, it could be an event of person, it could be an event of city, as we saw in Sarah's example. So what is the benefits of a strongly typed language, right? So in general, you don't necessarily have to use a strong typed language, but you can use it as a tool to work and think with. So even when you're doing programming in other languages, you can apply this type of thinking. And why do I think it's important? Or what is my premise for saying that? Well, our parents seem to think that it's important, since most of us, when we grow up, have one of these, which is basically the programmer's handbook to types, right? A type will only fit in one slot. So in Haskell, so I will just give you like a short introduction. So the interesting thing about this, I might actually give you more questions than I will be able to answer if you're not familiar with this type of thing. So the idea is that please interact with me later, and there will be tons of time for questions, and then we'll go through it like we can interact in that way. So there's two types of polymorphism in Haskell. We have parametric polymorphism, and we have ad hoc polymorphism. This is an example of parametric polymorphism, and it reads like ID : reads as has type of for all A to A. And the interesting thing about parametric polymorphism is this only have one implementation. Like it can't be any other thing. There's only one implementation to do this. And that is to return the thing that you get. Because we know nothing about A, so therefore we can't make any decision based on A. Oh, I can see I kind of copy-pasted something else. And the ad hoc polymorphism part is this. There's sometimes it's actually a type signature. You can choose, depending on what you're doing, you can explicitly have the for all, or you can ignore it depending on what language extensions you have added. So the add function is, you read that as add has type of num A or constraint to A for A to A to A. So that means that this is a function that will accept any A as long as I know that that A implements what we call a type class num. Okay, so I'm very fortunate that we had the first speakers actually teach you everything there is to know about RxJS. So I set out actually to take one of their tutorial examples and then re-implement it in how it would look in Haskell Reflex. So it's an example where they get some DOM, they create some observables, they map over them to assign some state, so it's a counter example. Yay. A decrease button, they find an input, they merge all their streams into one stream, and they then, whenever like one of these happens, they apply that function over the current state. It's actually quite interesting. Like there's, if we get into it, like there's deep knowledge about what a function actually is, and it's a common design pattern, if you will, in these kinds of things, like the event, since the A, event T of A, and it can be any A, that can be a function. This is what they're doing here. You don't really think about it. So these streams are actually returning functions. A function that takes an event, a state, and then it does something with that state. So whenever this event happens, this is why the event is actually a change function. And then they subscribe to that and then apply that into the DOM. Okay. So I have some demo code here. So this is just a basic example of what it is. I'm literally just implementing what it is. So you can increase, decrease, they have this state. It does exactly the same thing as they had. So let's go through that and try to break that down. The first thing I have is just setting it up. I can run a local server, as you know, and familiar with your own development framework, like, oh, I'm doing something and I can reload it and it applies. I have my main widget. My main widget consists of some stuff. It's not interesting right now. What's interesting is reflex example 1. Right. So this is the Haskell implementation of the JavaScript code you just saw. Let's go over that for a minute. Most of you can probably read this. It should be pretty obvious what this does. This, however, seems a bit more funky. We are known for in Haskell to have symbol soup, or we just like bling, so we have dollars everywhere. So button is a widget that takes some attributes and takes a label. And then it returns. So if you look at attached types, normally you wouldn't actually write this. This is for educational purposes. So this is actually the type of thing that this returns. So the add on this side here is what's inside of the M. And M in this case is a monad. If people are interested in like more specific examples of monads, I'm happy to show them after the talk. So what we're doing here is I'm creating this M event T of modal, and then I have this thing. This thing reads as map. It has the name fmap because it's generic over all functors, and we choose weird names for things. But these names are coming from mathematics background, so they actually do have meaning. But if you're coming as a programmer, you would probably prefer something as mappable. So everything that implements functor is mappable. This widget is mappable. So I first do, like I'm saying, map over this M, which means I'm going inside the M. Then I'm having this funny business. I probably need my hands now, though. But the half, like the less than dollar, is a shorthand. It's if you write it out more, we have like a lot of these combinators. It's literally saying fmap constant of the value on the left. So I'm basically saying, I don't care what this value is, just return this value instead. And then let's look at how add is defined. Well, add is some function that has the type of model to model. Well, what is model? Well, model is defined up here, so I have a strong type. So my model is a record. Think about this as an object with two fields, count and input value, and these then have type. And I construct like how to get an initial model. So that's add. So it takes a model. This is deconstructing. So you have like in modern JavaScript, you have deconstruction as well now, which is quite nice in many cases. So here I'm saying this dot dot means give me all the fields inside of this thing, which means I have access to count and input value in this scope. So I'm taking the model, and this is the add M is saying the entire thing. So I'm taking the entire thing, updating what count is with count plus 1. The same thing we do for decrease button, and it returns an unsubtract, so event. And then the last thing is I have like make input, and make input is creating a text input form. It returns a record of some stuff. I'm pulling out whatever the value is of that thing, and then I'm f-mapping. So here, this dot here is function composition. In Lodash and other Ramda frameworks now, are you familiar now with doing function composition? So, and the trick about Haskell in many cases is just learn how to read these things. So read it as after. So this really reads fmap set input after text input mapped of make input. So if we look up here and see what set input is, set input takes a text, then a model, and then returns a model. So up here we discarded whatever the value was from the button. Down here we actually care about the input value. So I'm mapping this over, and it returns a function that then waits for a model. And the reason why this works is because by default everything in Haskell is curried, which I think most people are familiar with as well now. Like currying function is a function that instead of taking all its arguments and returning something, every time it gives it one argument, it returns a new function waiting for the next argument. Have you seen this? I can show you an example in in JavaScript, right? So this is basically what curry would mean. And with modern fat arrow syntax, it's quite easy to make like some homegrown curried functions, which you can apply this way. Like you can kind of bake in arguments one at a time, and then you can apply them later on. So you can kind of construct functions from simpler functions. So here is actually the state folding thing you saw before. So fold dyn takes a function that steps over the incoming events and the current state, as we saw that they have the scan function in RxJS. It takes the initial model, which is basically a model of 0 and empty string. This leftmost is merge. So interestingly enough, leftmost is if I have a list of events, it will collapse them down into one event. So they had merge. But this is saying if two events are firing at the same time, pick the leftmost. Because there's different actions that you can do depending on events firing and what to do about them. And you can actually solve that in RxJS. So there's examples of RxJS actually doing something wrong because it doesn't understand. You get like some weird flash of context. Down here, we are doing, if you see that they're kind of like, oh, we don't actually want to do more work than necessary, so they check whether or not the value changed. They also use this function, the distinct until. This is kind of the same thing. In order to do less work in the browser, we're like, did the value actually change? And then actually touching the DOM. It's the same thing doing here. So I have my state. My state is produced from my fold dyn. It's a dynamic of model. I then map count over it, because each field in Haskell is a function that takes the thing and returns that attribute. So you can think about it as if you had an object, model.count or model.input value. And then I'm just saying, like, don't say anything unless it changed. And then I just display them in the browser. Which gives you this, that you see. So just to show like it's quite flexible and hopefully readable in some sense, even though a lot of this is esoteric. And it's like not saving the best for last. It's like saving the talk that requires the most amount of alcohol, I think. So if anybody's familiar with the Elm language as well, they have like the Elm architecture stuff, which is very popular. So like I try to mirror how some similar to the Elm architecture would actually look, instead of just having functions that you can merge or compose. Then they normally always say, oh, I have some data structure, and my data structure is defined as a sum type. I can increment, decrement, or I have a value, and the value actually has a field of text. And then I define one update function that says, like, OK, I pattern match on my action. Like a function, it takes the action, then a model, and then returns a new model. Inputs is passed in here. You pattern match on it, saying if it's increment, do this business. If it's decrement, do this other thing. If it's value, then set the input to that value. Everything is exactly the same thing. The only thing that changed was this update, and the fact that now instead of just having any function, I'm like locking it down to a specific thing. So, and this is kind of like a trade-off in flexibility, because if I just write inline functions, I can more or less do anything at the location of what I want. But if I write it in this way, I kind of limit myself. Like it's kind of closed set now. I only have 3 actions. Interesting, actually, the reason why these are called sum types is because of the cardinality of a type. And cardinality basically means how many members, value level, are there of a specific type. So in this case, it has 1, 2, and if there's one argument, it has the cardinality of that thing, right? So a Boolean value has 2 because it's either true or false, so 1, 2. If you have a product type, which would be a tuple, we don't have tuples in JavaScript, a pair of bool bool, that is that's a product. That's why we are calling it sum types and products, because it's literally the amount of members you can have of a specific type. So if you have a pair of some things, the amount of members you can instantiate that with is how many choices do I have for one of them and how many choices do I have for another, and you multiply them. And another thing that most people actually don't realize is if you have a function from A to B, the amount of implementations of that function is however many things B can be to the power of A. So there's some examples here. This is unit, it's one thing, bool, two things, data type maybe, so it's parameterized data type, and then some type of fruit, which has three things. And here's the cardinality of these things, like you can see. And so it might seem weird at first, but actually knowing some of these things give you like a very set like basis. Like normally when I talk to people and there's like, why do you care? Think about combinatorics, right? If we have, what is it, 5 factorial, that's 120. What if I have 10? That's 3.6 million. Like the number of things that we kind of get is kind of exploding, and it's hard for us as humans to have in our heads, so it's nice that we can constrain it. And so this is kind of like a, well, let me actually check. Curse your phone. Oh, fair enough, 20 minutes, actually a good time. So like we use this, and it's by no means a perfect solution, but the things that I can learn in Haskell and some other things that I didn't, like if you ever heard them name monoid as well, or semigroup, and all of these abstract algebra concepts, they're kind of very powerful abstractions to know, and you can apply them everywhere, right? So when I see some interface in Haskell, or I see something you do in JavaScript, oh, it's just this thing, or that thing. So I know how to interact with it, but I don't necessarily know what the thing is. So the problems with this thing is like the JavaScript backend is kind of slow. There's other alternatives. They are working on compiling to native, so you can make web apps, Android and iOS this way, which is pretty cool, and it will hopefully only get better. But it's still kind of slow in the browser, particularly parsing. Parsing is one of the slower things. So I'm kind of like greatly looking towards WebAssembly that hopefully would enable us to bring like more languages to the browser than just JavaScript. And as I said, like this is a very small subset of what there is to know. I can talk about this forever, so if anybody's interested in anything or more theory, then just come to me afterwards. Any questions? Well, I can actually demo our website. Our entire website is written this way. So like you at TweetDeck only use like subsets of RxJS. Our entire thing is actually written like this in Haskell. Like this is the front page, all the data incoming, and this is like a view of trees that I'm rendering based on what data and what's selected. So it is possible to actually do meaningful work with this. And let me smash my browser. So we have like 600 units in the field, and I can subscribe to all of them. It shouldn't be possible though, but it's so this is like a real-time view of these batteries that I talked about before. And right now I'm subscribing to roughly like 1.5 kilowatts. No, 2. We have a lot. And this is just, it does make sense. Like the values you see on the graph does make sense because I'm aggregating them as going, and it does make sense for individual units. But right now I'm subscribing for real-time events for 650 odd batteries out in the field in the browser. And we can kind of use like really weird things like I'm in a parser in Haskell. I'm also importing that in the browser to parse logs in the browser for DevOps and stuff like that. Yeah, let's kill my browser. It does not like. Oh yeah, actually, this is one of the creators of RxJS, and he's pretty fruity. So Eric Møller. So I thought like a shout out to him.